Welcome to this explainer. Look, if you're operating or maintaining heavy offshore machinery, you already know the stakes are incredibly high. Picture this, you're dealing with a massive crane overload, and at the exact same time, your primary control system just fails. It's literally the ultimate nightmare scenario in offshore lifting. So, how does the equipment protect itself, the vessel, and most importantly, the crew? Well, today, we're going to do a deep dive into the MacGregor 100-ton active heave-compensated crane failsafe systems. We're going to unpack the exact layers of defense engineered to save the day when everything else goes completely sideways.
Okay, let's dive into this mental roadmap. First, we'll cover understanding MOPS basics, then whip and main winch mechanics, followed by the battery backup lifeline, and finally, emergency stop protocols.
All right, Section 1, Understanding MOPS Basics.
Let's set the stage and transition into our very first layer of defense. Imagine you're right in the middle of a heavy lift. The load suddenly spikes way beyond the crane's safe working limit, and your automated systems are completely unresponsive. That brings us directly to MOPS, which stands for the Manual Overload Protection System. It's specifically used when the crane is overloaded and the primary control system isn't dealing with the situation correctly. Think of MOPS as your ultimate manual safeguard. It's the system of last resort when the software and standard controls have bowed out, relying entirely on physical hydraulic principles to take over.
Before we get into the exact mechanics of how this works, it's really important to note that every single technical parameter, battery spec, and emergency protocol we're unpacking today comes directly from this official MacGregor user manual documentation. By basing our explanation completely on the manufacturer's actual engineering guidelines, we ensure that the takeaways here are 100% accurate and compliant with the systems you'll actually see in the field.
So, the crucial point is understanding the sheer drastic reality of what happens when MOPS is activated. When an operator triggers this system, it leads to the winch simply paying out. This means any load currently on the hook is going to drop, and it will keep dropping until gravity takes over and some physical barrier, like the seabed or the deck, finally stops it. I know it sounds severe, but in an overload scenario that threatens to pull the entire crane or vessel down, sacrificing the load to save the ship is exactly what the system is engineered to do.
Moving right along. Section 2, Whip and Main Winch Mechanics. Now that we conceptually understand what MOPS does, let's peel back the next layer and look at the actual hardware. How did the specific winches inside the MacGregor 100-ton physically react during this kind of crisis? And this brilliantly illustrates the differences and the shared engineering between the two systems. On the whip winch MOPS, it works by activating a single MOPS on-off valve. On the main winch, since it's a much larger mechanism, it activates a complete set of valves. But look at what they absolutely share. They both ensure that the brakes are released and the winches can spin freely. And they pull this off by utilizing stored pressure from a bank of accumulators. Let's move to the exact sequence and see how this builds step by step into a really elegant micro-narrative of survival. Step 1, the operator manually activates MOPS. Step 2, because we might be in a total blackout and the main hydraulic power unit or HPU might not be running, the system utilizes that stored accumulator pressure we just mentioned. Step 3, this pressure forces the brakes to release and compensates for any internal oil leakage. And finally, Step 4, the oil is allowed to flow freely. As long as there's tension in the wire pulling on the hook, the winch will simply pay out. It is a beautiful, purely mechanical failsafe.
Next up, Section 3, the battery backup lifeline.
Okay, so releasing those hydraulic valves requires at least a tiny spark of electrical power to trigger the solenoids. So what happens if the main control system power is completely dead? This brings us to our third layer of defense, redundant power. Inside the crane's CC100 system, there is a dedicated, independent battery pack. The hardware specification is specific. It consists of two 12-volt batteries connected in series. The sole purpose of this battery setup is to serve as a lifeline. If the primary control system power fails, these batteries step up to drive the MOPS valves. Because without this battery pack, activating MOPS in a dead ship scenario simply wouldn't work.
Now, what's really interesting about this slide is this single number, 15. The manufacturer specifically mandates that there must be enough power in that battery pack to ensure at least 15 minutes of guaranteed operation. This isn't just an arbitrary specification, it's a literal metric for survival. It gives the operator a guaranteed 15-minute window during a total power failure to recognize the overload, trigger the manual overload protection system, and let those winches safely pay out the load.
Finally, Section 4, Emergency Stop Protocols.
We've talked about mechanical failsafes and electrical redundancy. Now, let's transition to our final layer of defense, the hardwired human override, better known as the emergency stop circuit. This circuit doesn't rely on complex software logic to function. It physically breaks the electrical circuit. MacGregor places these switches in highly strategic locations. You've got one right in front of the user in the operator cabin. There's another at the crane king, right at the starter panel. A third is located in the crane pedestal, and importantly, the crane in service mode key switch is also hardwired directly into this emergency stop circuit. That ensures maintenance crews have the exact same overriding safety authority as the main operator.
So what happens the millisecond someone hits one of those buttons? It triggers an immediate cascading sequence of events to freeze the machinery. Step 1, the switch is activated. Step 2, instantly all hydraulic power unit pumps are commanded to stop, completely killing the main muscle of the crane. Step 3, power is entirely disabled to the control valves. And Step 4, an alarm is immediately generated on the operator panel screens inside the crane cabin, letting everyone know a hard shutdown just happened.
And I want to highlight one specific parameter in that shutdown sequence. 24. When that emergency stop is hit, it is exactly 24 VDC, or volts direct current, power that is instantly disabled to all control valves. By physically cutting this 24 VDC control voltage, the system guarantees that absolutely no stray digital signal or random software glitch can inadvertently cause the crane to move. It's a brilliant, definitive stop to all automated operations.
We've really covered a lot of ground today, looking at the mechanical payouts of the MOPS winches, the 15-minute 24-volt battery lifelines, and a hardwired emergency stop circuits. These are the systems that protect lives when things go wrong. So I'll leave you with this final thought to test your knowledge. If the main control system on your crane fails right now, do you know exactly how your layers of defense will react? I really hope this explainer has helped cement those crucial details into your memory. Thanks for joining me, keep learning, and stay safe out there.